today's class, you are set, right? Now, for today's class, we'll be looking at, we are still on shear force and bending moment diagram. Still on shear force and bending moment diagram. But now, we want to look at another aspect in shear force and bending moment diagram. Are you with me? I said, we want to look at what? Another aspect in shear force and bending moment diagram. And this question will definitely come out. It is a must. If it can be given that draw shear force and bending moment diagram, so be expecting this also. Are you getting me? Now, from here, we've looked at this previously, but we've not solved yet. Now, the question says that, I don't know if you are in the last class, for those of you that are in the last class, this was, we've been able to draw the shear force and bending moment diagram for this given beam, right? You know, we said, given this beam, Roman figure 1a, or question 1a says that, calculate the support reaction. These are the support reaction, right? 1b says that draw the shear force diagram and the bending moment diagram. This is my shear force diagram. This is my what? Bending moment diagram. Now, what if you have your question and the question says that determine the maximum bending moment. You know, see what I wrote on the board. I said shear force and bending moment diagram, indicating important points. Indicating what? Important points on shear force and bending moment diagram. The first one is what? Location / value of maximum bending moment. Are you getting me? The first important point we need to know is what? The location / value of maximum bending moment. Number 2, location of point of contraflexion. Now, go back to bending moment calculation. Go back to, don't need to go back there, you can only see it on the board. Go back to bending moment calculation. I believe you know how bending moment works, right? We all here, we already have the idea on how bending moment works, right? Now, looking at your bending moment diagram, what I want you to do for me is that identify which one is the greatest value among these values. I want an interactive class. Are you with me? So which one will be the greatest value? Which one is the greatest value among these values? You know, I'm having 30 kilonewton meter, I'm having 17.5 kilonewton meter, I'm having 20 kilonewton meter, right? And I'm also having 0. This is the origin, this is also the origin. But the question is, what is the greatest value of bending moment? 30, right? This is 30. But now, by calculation, we got 30. Does it mean that at what point, you know, this 30, we took bending moment about t, meaning distance 4 meter, right? We took moment about t, meaning the distance is what? 4 meter. That's what gives us this 30, right? The next one, 17.5. We took moment, or we did bending moment calculation about d. What's the distance? 5 meter. The next one, what am I having? 20 kilonewton meter. We did our bending moment calculation at b. What's the distance? 6. How do you get 6? 4 plus 1 plus 1, right? Now, you now said after this calculation, I'm getting the greatest value to be 30 kilonewton meter at distance 4 meter. Does it mean that if I take bending moment calculation at 2 meter, or does it mean that taking bending moment at distance s will be the greatest value of bending moment for this given beam? Am I communicating? You know, the same way you took bending moment at a, at 5 meter, at 6 meter, you can also take bending moment at 2.5 meter, true or false? Right? You can also take bending moment at what's the total length? This is 7. You can also take bending moment at 6.5, right? You can also take bending moment at 6.9. It is your choice. At any point you can imagine that you have in this beam, you can take bending moment, true or false? Yes, sir. So when we now say that the location / value of maximum bending moment, it's still the same thing we are doing. It's still what we know we are doing. You know, in this case, looking at what you have here, let's relate it to this number 1 point, important point of shear force and bending moment diagram. Looking at this, what is the location and what is the value that the greatest maximum bending moment occur? What is the location? When I say location, meaning distance. When I say value, meaning magnitude. So let me ask that same question again. Looking at this beam, based on the diagram we have on the board, what is or where does the location of maximum bending moment, at what distance does it occur, and what is this value? Looking at what you have here, it is what? It occurs at 4 meter, and what the value? 30 kilonewton meter. But with what you have here, you can't just conclude that the location is 4 meter and the magnitude is 30 kilonewton meter. You can't just conclude. You have to solve. Are you getting me at all? You have to solve. And even in the last class, we've explained all this, you look at all this. But just for better understanding, so I need to explain that. All right, now we said location slash value of maximum bending moment and point of contraflexion, they are synonymous. They are what? Synonymous, right? Meaning that the difference is that you obtain the location and the value of maximum bending moment using your shear force diagram. Are you getting me? You obtain the location slash value of maximum bending moment using your shear force diagram. For point of contraflexion, you obtain it on what? Your bending moment diagram. Now the question is, at what point? We've discussed all this, but for better understanding, for sake of understanding, let's say this is A, this is B, this is C, this is D, this is D, this is E, F, G, and H. Now from here, please, I want interactive class. I love interactive class. When my class is interactive, there's more energy. You get? When there's energy, it becomes lively. So you just looking at me. I don't want that. Now from here, I said let's denote this as A, B, C, D, E, F, G, H. What I want you guys to do for me is that observe this shear force diagram. Observe this shear force diagram. At what point? You know, A is a point, B is a point, C is a point, up to G, right? This alphabetical arrangement or this alphabetical order, they are a point. Now, at this point that we've indicated on our shear force diagram, at what point do you have shear force changing sign? At what point? Is it point A? We've indicated it already. Just say it. Is it point A? Is it B? Is it C? At what point? At point B, right? If shear force is changing at point B, it means the value here is what? 0. Meaning shear force is 0 at this point. Are you getting me? Yes, sir. If you are saying shear force is changing its sign from positive to negative at point B, it means shear force is 0 at this point, right? So what it means is that you can rephrase it in two ways. The first one is you saying that maximum bending moment occur at the point where shear force changes sign, meaning positive to negative, or where shear force is equals to 0. Are you getting me? Let me repeat myself. I said you can now rephrase it now. You say maximum bending moment occur at the point where shear force changes sign. When we say it changes sign, meaning from positive to negative. If you are not saying that, you can say that it occur where shear force is 0. You are still saying the same thing, right? You are still saying the same thing. Now, we're saying that shear force, we're saying that we are going to have maximum bending moment here. It means when we say location, meaning I want to know the distance of X at this point, right? By location, this is what we are saying. You've already identified that your maximum bending moment will occur at this point. Meaning, let's say from here, this is what? X meter, right? Your interest now is what is X meter? What is what? X meter. But looking at this O beam, from A to C, what do I have? 4 meter, right? From A to C, I'm having 4 meter. Since this is your interest, meaning the point where maximum bending moment is going to occur, you getting X equals to 5 meter. Is it correct? No. It is not correct. Just because if from here to here is 4 meter, and you know that this is your interest, meaning that any number you'll be getting for location of maximum bending moment must be lesser than 4. Must be what? Lesser than 4 or below 4. Now the question here is, how do I know this number? How do I determine this location? Or how do I know this number? You have two methods. You have what? Two methods. In textbooks, you see the first method, but what your lecturer will taught you in class, you see the second method. But you love one than the other. Reason is because one is faster than the other. Though both of them, they are very simple. Very simple. Are you getting me? But I know that you love one than the other just because the other one is very, very simple. It's not saying it's very simple. It's faster. Yeah, it is faster. All right. Number one way of calculating the location. Okay, this is it. Now we already know that the maximum bending moment value is going to occur here, right? Meaning x meter. Since he said x value will be lesser than this 4, let's just do an assumption saying x is equals to what? 2 meter, right? Or let's say x, better still, let's say x is equals to 2.7 meter. Let's say x is equals to 2.7 meter. You know, you've answered location, right? Any question? Let's say x. What do you say? I said let's do an assumption. I'm going somewhere. Let's do an assumption. Let's say x equals to 2.7 meter, right? Meaning, out of this question, this is how you see your question in the exam. Meaning, the question says that calculate location / value by location. Meaning, your location is what? 2.7 meter. How do you now get value? The bending moment calculation you'll be doing. Now take bending moment about that point. Take bending moment about that point. Right? Alright, let's see how it works. By the time you start solving, you understand better. Now, from here, your first method, the first method, we have two methods in finding the location of maximum bending moment. Have it in mind that you must know your location of maximum bending moment before knowing the value. What value simply means is that you want to take moment about that point. You know, you taking moment, we said moment is what? Force times perpendicular distance. You say you want to know the value, taking moment first. What becomes the distance, right? You don't know. So meaning that when it comes to question like this, your first task is what? Calculating the location. When we say location, meaning distance. Now I said we have two methods in finding the location of maximum bending moment. The first method is what? Using similar triangle. Number two method is what? Sectioning the beam. Now from here, you can decide whichever method you want to use. But this is the easiest one. This second one is the easiest one. So I'm saying that when you read on your own, in textbooks, the commonly used textbook for strength of material or for structure generally, it is Archimedes, right? So if you check Archimedes, you see this guy using similar triangle. But what I don't know if the lecturer taking you guys, but Engineer Ogunbadi, right? This is what Engineer Ogunbadi is going to teach you guys. So this is what you'll be taught in your class. Alright, now the first method, let's look at the first method, which is what? Using similar triangle. Now, you using similar triangle, what it means is that, look at your beam. You know, this is my interest now, right? I want to know this value of x. We now said, using similar triangle, what it means is that, by the time you look at this beam, you have triangle, right? You know, this shear force value, they are shapes, right? Square, you have it in different shape. For point load, is in square. For UDL, slanted. For trapezoidal load, or you say for UVA, it has another shape, right? So when you are saying using similar triangle, meaning that looking at this shear force diagram, my focus is what? Triangle. Or what I want to pick out from this shear force diagram, it is a triangle shape, right? Now looking at this shear force diagram, how many triangles do you have? You have the bigger one and the smaller one. Right? This is the bigger one, say 1. The smaller one, say 2. Are we together? This is the bigger one, while this is the smaller one. So can you see what they are saying? Using similar triangle, meaning that you can relate this first triangle with this second triangle. Any question on that? We can what? Relate this triangle to this what? Second triangle. Now from here, let's bring out, are we together? Now from here, what I just want to do, since you already know that you are using similar triangle, the shapes you are taking here, just triangle, meaning this first one and this second one. So I'm interested in this part of the beam, true or false? Meaning from A to C. What is the span of A to C? 4 meter. I'm interested in this part. I don't have any business with this one, just because I'm not having a triangle shape. But this, I'm having a triangle shape, which is this first one and this second one. You know, from similar triangle, this is what you are saying. You have two right angle triangle. Say this is let's say this is figure 1. By figure 2, let's say you have this. This is 90 degree, right? This is also what? 90 degree. True or false? This is 90 degree. This is also what? 90 degree. So you are relating the two sides. This is figure 1. I'm having, this is hypotenuse. This is what? Adjacent. Assume, let's say we are having an angle, say theta. We are also having an angle, say theta, right? You know, you can see how we are going back to elementary mathematics where we are doing strength of material. So that's how it works. When you now get to let's say advanced level, probably 400, 500, your lecturer will not be telling that we got that from year 1. Can you see how it works? So now from year 2 now we are going back to elementary mathematics. From elementary mathematics, I know that I have this very guy, which is what? Right angle triangle. From right angle triangle, this is my adjacent, right? This is my hypotenuse, and this is my what? Anywhere your angle of inclination is facing becomes your what? Opposite. So this is my what? Opposite. This is hypotenuse. And this is adjacent, right? What's the law governing this right angle triangle? That's SOHCAHTOA, right? SOHCAHTOA and Pythagoras theorem. So by SOHCAHTOA, we are saying I have SOHCAHTOA. What does this mean? Sin theta is equals to opposite over hypotenuse. The other one is what? Cos theta is equals to what? Adjacent over hypotenuse. The last one, what do I have? Tan theta is equals to opposite over what? Adjacent. Call this 3. You know, you can use any of these when it comes to trigonometry. Whatever side you have, let's say in your right angle triangle, if I'm having opposite and hypotenuse, I'm using sin theta, right? If I'm having adjacent and hypotenuse, what am I using? Cos theta. If I'm having opposite and adjacent, what am I using? Tan theta. You get? I'm using what? Tan theta. So what it means is that by the time we bring out these two triangles from this Shear force diagram, if I'm having opposite and hypotenuse, what will I use? Sin theta. If I'm having adjacent and hypotenuse, it becomes what? Cos theta. Lastly, if I'm having opposite and adjacent, what do I have? Tan theta. Tan theta. Now let's bring this diagram out. Let's bring this diagram out. From this diagram and this shape, from what length? From what length are you considering in your shear force diagram? 4 meter. Your 4 meter. What type of load is it loaded with? A UDL. So that's an hint for you. Whenever you have a beam subjected to a UDL, most likely you have maximum bending moment. Are you getting me at all? When you have a beam and that beam is subjected to a UDL, most likely you have what? Maximum bending moment. This is because your positive axis is going to cut the origin, meaning it is changing sign from positive to negative. And when it is changing sign from positive to negative, meaning maximum bending moment has occurred. So that's it. So also note that. So from here, let me bring this guy out since that's my interest. So I'm having this UDL, right? This is A, this is C. What's the intensity? 10 kilonewton per meter. Now from here, I have this. I have this. This is positive, this is negative, and this is the length is what? 4 meter. What's your interest? This guy, right? This is what? X meter. Have we included all values? So when you are doing this, it means anything you have here, that's what you are still repeating. Nothing is changing, right? Nothing is changing. So look at, say this is 1, say this is 2. Look at 1 and 2. Are they the same? We've included all, right? Have we included all the load, the support, the diagrams? Which one have we not included? Okay, what's the value of RAY? RAY is equals to 27.5 kilonewton meter. Alright, sorry, kilonewton. Now from here, from this diagram, you are giving that A to C. You know, this is my total length, which is from A to C. It is spanning what? 4 meter. Let's say this is C. Meaning from A to C is X meter. If from A to C is X meter, call this D. From, okay, let's say this is from here, this is it, A to C. This is it here, A to C. This point that I want to get the value of S says C. Let's denote it as what? C, right? Meaning from A to C is what? X meter. Then from C to, let's give this B, right? Now if from A to C, you know, mathematically AC plus CB is equals to what? AC, right? Mathematically AC, or should it use B here? Okay, let's go in ascending order. Let's say I have B here and I have C here. Since this place is C, so at this point I just have B. Okay, it's okay like this. Now from here I said mathematically, what does this imply? It means AB plus what? BC is equals to what? AC is equals to AC. We've not included all values. Do you know the value we are yet to include? The value of this diagram, the value of this triangle at the y-axis. So what's the value of this diagram? What's the value of shear force at this point? 27.5. So I have 27.5. So meaning for this side, I have 27.5 kilonewton. For this other triangle, what's shear force value here? What's the value of shear force? Are you sure it is 30? This is for bending moment. In our last class, those of you that are here, 12.5. Alright, you know it was negative 12.5, but you don't need the negative. So write 12.5. Right? 12.5. None of you including the unit. There's no need of you including the unit. So for this one, what do I have? 27.5. What about this one? 12.5. Now I said mathematically, I'm having AB plus BC is equals to what? AC. Now I want to get BC. Say this is equation 1. Say this is what? Equation 1. I want to get BC. Meaning make BC the subject of the formula. What do you have? Please let's do this together. I have BC is equals to what? BC is equals to AC minus AB. Call this equation 2. Now let's input values. What's AC? 4. What's AB? X. So you're having that, therefore BC is equals to 4 minus X meter. 4 minus what? X meter. So what do you have here? You have what? 4 minus X meter. Now let's relate these two diagrams. You know, this is your first diagram. Let's say you are doing centroid. This becomes the first component. This becomes the what? Second component. Now for this first component, let's relate it to this figure 1. Are you getting me? For this first component, which is your triangle, let's relate it to figure 1. You relating it to figure 1. How many sides does it have? You know, from figure 1, I'm having opposite, hypotenuse, adjacent. Right? You relating it, how many sides does it have? Wow. Look at it very well. You are relating this first component to figure 1. Meaning I want to identify which one is my opposite, which one is my hypotenuse, and which one is my adjacent. Now look at it very well. How many sides do you have? 2 sides, which are what? Opposite and adjacent. Do you have hypotenuse? No hypotenuse. What about the second one? Say you have this diagram as your second component. How many sides do you have? 2 sides, which are what? Where do we have 12.5? The opposite, right? In this case now, okay, let me write the value that you guys got for me. This is your figure 1, right? By figure 1, what do I have here? 27.5. Let me make this bigger. This is theta. This is also what? Theta. This is what? Figure 1. This is figure 2. Now from figure 1, we've identified that relating this first component, say this is your figure 1, say this is your figure 2. Relating this first component as your figure 1. You know, from figure 1 initially, I'm having opposites, I'm having hypotenuse, and I'm having what? Adjacent. Now, I want you to do this simple identification for me. From this figure 1, how many sides do you have? Do you have all the 3 sides? No. Just 2 sides, right? And these 2 sides are what? Opposite and adjacent. What's your opposite in this case? 27.5. What's your adjacent? X meter. So substitute. What do I have? I have 27.5. Then what? X meter. Similarly, the same way you identify for figure 1, also do that for figure 2. So tell me, how many sides do you have? Do you have opposite, hypotenuse, and you have opposite and adjacent? Now, what's your opposite? 12.5. All right. What's your adjacent? This is what? 12.5. This is 12.5, and this is what? 4 minus x meter. We now said that you know, the basic law that govern right angle triangle, there are 2, right? The SOHCAHTOA and the Pythagoras theorem. So we are using SOHCAHTOA. We said, since from these 2 figures, okay, let's do it this way. I'm using what? SOHCAHTOA, meaning equation 1, equation 2, and equation 3. You know, you use any of these equations depending on the size you are having. So now, looking at your figure 1 and figure 2, out of this equation, which one am I using? 3, right? I'm using what? 3. And by equation 3, what does it say? That theta is equal to what? Opposite over adjacent. Meaning, as far as this question is concerned, I'm making use of what? Equation 3, which is what? Tan theta. Which is what? Tan theta. Now, by tan theta, that becomes what? What do you call it? Tan theta is equals to 27.5 over x. Call this equation 1. This is from figure 2. You got equation 1 from figure 2, right? Now, moving on to the next figure, which is figure 2. And theta becomes what? 12.5 over 4 minus x. Call this equation 2. Call this equation 2. Now, your next step, after all this process, your next step is what? Equate equation 1 and equation 2. Equate what? Equation 1 and equation 2. Why are you equating equation 1 and equation 2? You know, from equation 1, it reads as tan theta is equals to tan theta, right? Which implies 27.5 over x is equals to 12.5 over 4 minus x. Right? From equation 1, this is your tan theta. From equation 2, this is your tan theta. Meaning that tan theta is going to cancel out from both equations. Now, call this equation 3. Call this equation 3. Initially, I want to calculate the value of x up to equation 3. What are you going to do? Cross multiply. Initially, I want to get the value of x up to equation 3. What are you going to do? Cross multiply. By the time you cross multiply, we then have 27.5 on into bracket 4 minus x is equals to 12.5x. 12.5x. Now, let's open up these brackets. What do we have? Now, from here, I said from equation 3, cross multiply, right? Now, multiply this. What do you have? 27.5 times 4. What do you have? 110. All right. 110 minus 27.5x equals to what? 12.5x. From here, collect like term, right? Meaning 110 is equals to 12.5x plus 27.5x. I have 110 equals to 40x. From here, divide both sides by 40. Therefore, x equals to 2.75 meter. X is equals to what? 2.75 meter. Now, when you say x equals to 2.75 meter, what are you saying? It means the value of bending moment, it can only get the maximum value at x equals to 2.75 meter. Are you getting me at all? Yes. This is the point where you have your maximum bending moment. If you do your bending moment calculation at 6.9, the value will be greater than 6.9 value. Just because by calculation, you've seen that x equals to 2.75 meter. So what this means is that to get maximum bending moment, as far as this question is concerned, you can only obtain the value when x is equal to 2.75 meter. What if I calculate the value of bending moment at x equals to 5.5? Will the value at 5.5 be greater than this? No, it can never be greater, irrespective of the distance. Irrespective of the distance. You know, by calculation, I'm having 2.57, right? You know, I would have believed that the value of bending moment at 5.5 should be greater than 2.75, right? Looking at it, just looking at it in a normal way, I would have believed that the value at 5.5 should be greater than what? 2.75, but it does not work that way. I said normally.
Does it mean that as the
as the length increase, the bending moment value decreases? No, I don't think so. Well, probably, yeah. Okay, let's do it like this. You know, at 4 meter, what do I have? 30 kilonewton meter. At 5 meter, what do I have? 17.5 kilonewton meter. Probably it works like that. Yeah. That should be the reason. Are you with me? Can you see that when we calculated this value of x, which is the location where maximum bending moment is going to occur, we got the value lesser than 4, meaning we are correct. Meaning what? We are correct. If it is greater, you don't rubbish. It's something that you are seeing. From here, he said bending moment will occur at this point, x meter. You are not getting, let's say for instance, I'm getting 5.5. Looking at this, you can never have 5.5 below 4. Hope I'm communicating. So that's how it works. So this is your first method, and this method is called what? Using similar triangle. But the simplest method, which I know every one of us here will like, it is the one of sectioning. Use sectioning. It means that you're already doing advanced, you're already solving your beam, or you're already analyzing your beam in advanced level. When you say sectioning, what it simply means is that you are separating your beam. Right? Now, hello, are we together? Yeah. Now, when we say sectioning, you know, you are interested in knowing the value of x. By the word sectioning, it means from this point, trace it up. Why did I say trace it up? You trace it up, you have this, meaning you are sectioning your beam. Let's say this point. Okay, section your beam xx at a distance x. What did I say? Section your beam xx at a distance x. Meaning you are interested in knowing the value of x, but you are sectioning it xx. Meaning this is what? X. This is also what? X. Yeah, that's for sectioning. You know, read what I said. I said section your beam at a distance. Section your beam xx at a distance x meter. I'm saying xx just because I'm indicating my sectioning line with xs. You guys did technical drawing now, so you know what sectioning means. What if I'm saying section your beam 1 at a distance x meter, meaning I'm having 1 here, right? And I'm also having what? 1 here. That's it. For here, I'm using x. When using x, you are already going to the advanced level of analyzing your beam. Alright, now let's say you have xx. You are sectioning your beam xx at a distance x meter. Very simple, no stress. Meaning that, you know, once you've sectioned, you've separated this beam, right? Yeah. You've separated this beam. So this is part A. Alright, so let me use parts. Let's say this is part A. And let's say this is what? Part B, right? Now, once you've sectioned the total B, you've separated it to what? A and B, right? You've separated it to what? A and B. The one you are using is this A, meaning you are interested in part A. You're interested in part A, you are taking you are doing shear force. You are taking shear force at that point. You know, the first method is what? Using similar triangle. Number 2 is what? Sectioning the beam. Using number 2 is what? Sectioning of beam, right? Now, we saying you've sectioned this beam. You see the space that we are going to use to solve this one compared to the first one we did. Now, by sectioning, you are interested in what? Part A. So let's say you've sectioned, you'll be left with this, right? At the point of section, what will be the value of x? What will be the distance? At the point of section, what will be the distance? Is it 4 minus x? Is it 4? Is it x? Is it x minus 2? Look at it very well. When you're analyzing a beam, it's not about what I'm seeing. There's nothing add. I'm seeing this, I'm writing it. That's the meaning. Now, let me ask my question again. You are interested in part A. What's the distance of that part A? X meter. This is it. This is the point of section. You are choosing it up. Meaning, if from here to here is x, from here to here to is what? X. Now, this is your sectioning line. From your point A to your sectioning line, you have x meter. You have x meter. Meaning, you bringing out your beam, what you've sectioned. You know, this is what we are saying by sectioning. X. That's why I said section of beam XX at a distance x. At a distance x. Meaning you have this. Right? This is what? X meter. What do I have here? 10 kilonewton per meter. Say this is A. What's the value of RAY here? 27.5 kilonewton. Let's say this point that we've sectioned. Let's denote it as, say, shear force at XX. Why do I symbolize it, or why am I representing it as this? Representing it as this just because I'm doing shear force. I'm taking shear force at this particular point. And at this particular point, I've sectioned it as what? XX. Are you getting me? I've sectioned it as what? XS. Now, the shear force we've been doing, when we calculated, you know, if we want to calculate shear force, we simply say that I'm calculating the shear force value at each point on my beam. And how do I get this value? You calculate shear force value twice, right? And you know the condition. The previous force, the algebraic sum of forces behind the point you want to calculate, right? That will give you a first value of shear force. Number 2 value of shear force, what you've calculated plus the force you have on that point. Now, similarly, I'm taking shear force about point XX. That is shear force at XX. That becomes what? That will be what? By shear force, let's do this. That will be what? What's your shear force here? About this very point, what's your shear force? How do you get your shear force? Identify how many forces do you have behind? How many forces do you have behind? How many forces do you have behind? 2. I'm having 2. And these 2 are what? The support and the UDL. By support, what's the value? 27.5. By UDL, what's the value? By UDL, what's the value? Alright. What do you know about UDL? When you hear the word UDL, what do you know about it?
Uniformly distributed.
When you say uniformly distributed load, okay, what do you, by beam, you just want to take us back. You know this already. Let me ask my question. My question is very simple. Just understand my question. Now, I want to take shear force at this point. How many forces do I have? 2. Behind 2. I'm having this guy. You've identified that 27.5. You know, he said we are having area. The question is, what's the magnitude? Right? What's the magnitude? You guys told me what? 27.5. That's for the first force. The next force is what? This UDL. Right? This is what? What's the force of the UDL? 10x. That's it. Meaning, this 10 multiplied by the total distance. You've converted a UDL to a point load. So meaning that me taking shear force at this point, the upward force, take it as positive, 27.5. The downward force, take it as negative, which is your what? UDF. That becomes what? 10x. Equate this guy to 0. Meaning 27.5 is equals to 10x. Divide both sides by 10. What do you have? X
2.75 meter. Wow.
2.75 meter. Which one do you like?
Oh, is it because the question I was asking is every time we use this
Yeah, I would advise, as far as our school is concerned, all these are lecturer in this our school. Is whatever you are being taught in class, you should give them. If you can do over Sabi, some lecturer can penalize you, they can mark you down. So just observe the method your lecturer is using in class. If it is the first one, use it in the exam. If it is the second one, use it in the exam. But one way I know, what your lecturer will taught you in class is this second one. It is this second one. So use this second one. But can you see how it works? We make use of similar triangle. We got 2.75 meter. Using sectioning method, we also got 2.75. So this works for any types of beam. You want to get maximum shear force value. So you want to get the location of maximum bending moment. What we've done so far is just the location of maximum bending moment, right? Now, we are still solving a particular question. This is just the third question. Question will come and the question will say that, number one, support reaction, determine support reaction. We've done that. Number two, draw shear force and bending moment diagram. We've done that. Number three, determine the position. Or the question will say that determine the location, and some question will not stress you in the sense that the question will not say that determine the location of maximum bending moment. But some question will not say that determine the location and the value of maximum bending moment. What we've done so far now is just the location of maximum bending moment. You already know that for this given beam, the location of maximum bending moment is at a distance x equals to 2.75 meter, right? Now, what's the value of this maximum bending moment? What's the value? Meaning that you are still using this beam. When we calculated the location, we did shear force, right? The value, you are going to take moment about that point. You are going to what? Take moment about that point. Meaning that from this beam, or before then, what we've calculated x equals to 2.75 meter. You can write your final answer, which is the way I love doing mine. Okay, this is it. From here, from this point, this is my A, right? This is section XX, right? Let's say section XS, let's say E. Meaning from A to E is x meter. What's the value? 2.75 meter, right? From E to this last end of your shear force diagram, say H. Are you getting me? If from here to here is 2.75 meter, from E to H is what? How do you get E to H? 7 minus 2.75, and that's what? 4.25. 4.25 meter. Now, you want to come into conclusion and write your final answer, saying that you've gotten the location where maximum bending moment occur. You can write it in different ways, right? Now, this is how you write it. Therefore, the location where maximum bending moment occur, or you say where bending moment is maximum. But I'm saying that the location where maximum bending moment occur is at a distance x equals to 2.75 meter from the left hand support, that is A. From what? From x equals to 2 meter from the left hand support from the left hand support. And what's your left hand support? That is A. Now, you know, the way you are writing it now is that I'm referencing to the left hand support, right? What if I want to make use of the right hand support? That becomes what? The distance will be what? Not 4.25. Not 4.25. That will be what? 3.25. 3.25. You know, at the end, see what I did here? I said the location where the maximum bending moment occur. I calculated 4.25. I thought my support reaction was at this point. So that's why I calculated this value initially. I said the location where the maximum bending moment occur is at a distance x equals to 2.75 meter. You won't just stop there. You have to be specific. From what point? I'm not saying that from the left hand support. What the left hand support? A. Right? You know, this beam is having two support. So I'm saying that this distance occur from the left hand support, which is what? A. Now, what if you want to make use of the right hand support, meaning B? What will be your distance in this case? 3.25. 3.25. If from here to here is 2.75, then you want to make use of this distance. Is it 3.25? Okay, this is it from here. You know, the total length here is what? 4. Right? 4 minus 2.75 is what? That was 1.25. Right? Meaning from the place you've sectioned to C, what's the distance? 1.25. 1.25 meter. That was what? 3.25. This one plus this one plus 1.25. Meaning you have 3.25. So with this, you can write or at distance x equals to 3.25. 3.25 from what? From the right hand support. Right hand support. That is what? B. So if anybody sees this in your script, the lecturer will know that, okay, yes, 100, you know what you are doing. You know what you are doing. That's the meaning. Any questions so far? Yeah, what's the question?
When given the question, I don't need to. The question coming with the data, or you are the one that will analyze the data.
You analyze. That's what you are saying. Analyze your given beam. If you can draw, you know, initially, we don't draw the Shear and Bending diagram for you. No, you really want to draw it. So if you can draw Shear and Bending diagram, you should be able to do this. So, but with constant practice, all of these are very, very simple, right? So now from here, this is how it works. So this is how you use your first method, which is what? Using similar triangle, and the second method, which is what? Sectioning the beam. Sectioning the beam. So this is my location so far. What we've been doing this morning is just all about location. Now, let's get the value that will occur at this distance, which is what? 2.75 meter, and compare it to the values we have on this point. So by doing that, what do we have? What's the value of x? 2.75 meter. So now, what you are going to add here is a bending moment. Bending moment about xx. Now, you doing bending moment about xx. Let's do our bending moment calculation. That will be what? Let's do it together. That will be what? Calculate the value of bending moment at this point. That will be what? 27.5 times. You guys are forgetting bending moment. You don't understand again. I said from here. Initially, question says that what? Calculate the what? The value and the location. What we've been doing this morning is what? Location. Now, what do you want to do? Value. By value, what is the magnitude? You already know that at point x equals to 2.75 meter. That will be the greatest value of bending moment, right? But what is this value? Is this value 40? Is it 50? Is it 60? We don't know. How do we know? Let's solve. Now, how do you solve? Simply do your bending moment calculation at this point. The bending moment you've been doing since all these days. Do it at this point. I know how bending moment works. So let's do that together. What do you have? 27.5 times 2 point what? This is the total distance. This is the total distance. Times what? So you are saying that 27.5 times 2.75, is it clockwise? Is this force going in a clockwise or anti-clockwise direction? Clockwise. So you have positive. The next one is what? Minus what? Minus 10 times 2.75 times 1 over 2 times 2.75. So press this in your calculator. Individually, what's the answer? What's the answer for this and what's the answer for this? Do this separately, then this. So what's the answer? Don't tell me the total answer. The next one is what? What do you call it? 37.81. Right? So the difference is what? 37.81. You didn't come for the last class, that was right. That was right. One single value. We started about 2-hour question that will be solving this morning. We started it again. Just because of one single value. So I want to avoid that now. I don't want the same issue. Yeah, continuation. So now from there, can you see how it works? So this is bending moment about that particular point. Are we together? Meaning that you've answered the first question, which is what? Calculate the location and the value of maximum bending moment. What's the location? 2.75 meter. What's the value? 37.815 kilonewton meter. Now, what if that question says that indicate, draw the value? You already know that the highest value, the greatest value is 37.815. Now, what you have here, what you've drawn before, do you know that it is not correct? Right? It is not correct. In terms of how the shape is supposed to be. Like if the question says that indicate the maximum value on your bending moment diagram, indicate the value of the maximum bending moment on your bending moment diagram, or indicate the value on your bending moment diagram. If we continue, if we section this beam up to this point, this is what you're having. And looking at what you have here, you are saying 30 is greater than this point. Are we supposed to have that? No. This point is supposed to be greater than this. So you drawing your diagram again, which I don't think question mark comes like that. Only if they want to stress you guys. So you have this. Right? So you have something like this. This should be your what? 37.5. 37.815. And this should be your what? This should be your 30 kilonewton. Can you now see that this point is greater than this? Meaning that if we calculate the value of bending moment at 6.9, the value will be lesser than 37.815. If we calculate the value of bending moment at 5.5, any point of your choice, choose it, the value will be lesser than 37.815 kilonewton meter. So that's the concept behind location/value of maximum bending moment. All right, let's move to the next one, point of contraflexion.